Welcome back to DRX Learning Hub. Today's topic is redox titrations, an important group of volumetric methods used to determine oxidizing or reducing substances in pharmaceuticals. Redox titrations are volumetric analyses in which the endpoint is reached by a redox, that is, oxidation-reduction reaction between analyte and titrant. One species is oxidized and the other reduced. These methods are widely used for assay of oxidizable or reducible drugs, peroxide content, iron, copper, and so on. A redox reaction involves transfer of electrons. At equivalence, the number of electrons lost equals the number of electrons gained. The general stoichiometric relation using equivalence is N sub 1 V sub 1 equals N sub 2 V sub 2, where N is normality, or equivalence per liter, and V is volume in liters. Equivalents account for electrons transferred per mole. The titrant here is potassium permanganate, or KMnO₄, which is a strong oxidant. KMnO₄ is actually colored purple and acts as its own indicator. So, the pink or violet color persists at the endpoint. Typical analytes include ferrous ion, oxalic acid, and hydrogen peroxide, but with appropriate conditions. The medium is often acidic, usually using sulfuric acid, and for oxalic acid standardization, warm conditions are used, around 70 to 90 degrees Celsius. Alright, so let's talk about dichrometry. Here, the titrant is potassium dichromate, which is an oxidant. When it comes to the indicator or endpoint, we often use redox indicators like diphenylamine sulfonate, or sometimes we rely on back titration because, dichromate itself is orange, which can make things a bit tricky. Typically, dichromate titrations are used for determining ferrous ions, or Fe2+, and if needed, we reduce the sample to Fe2+ beforehand. Oh, and one more thing to note. Dichromate is usually used as a primary standard since it's a stable crystal. Moving on to iodometry and iodimetry, both of which really showcase the power of iodine in titrations. First up, iodometry is actually an indirect, or back, titration. Here, the oxidant present in the sample liberates iodine from iodide ions, and the released iodine is then titrated with sodium thiosulfate. For example, this method is often used in the assay of oxidizing drugs or peroxides. In contrast, iodimetry is a direct titration where iodine itself is the titrant, and the reducing analyte just consumes the iodine. For the indicator, starch is commonly used because it forms a blue complex with iodine. The blue color disappears at the endpoint, and just to be precise, starch is usually added near the endpoint, close to completion. Now, let's briefly touch on cerimetric and arsenic titrations. Ceric titrations, which use ceric ions, Ce4+, are employed for certain oxidizable substances, and the oxidant here is ceric sulfate. The choice of which method to use really depends on factors like reagent strength, selectivity, and of course, the sample matrix. Alright, let's talk about indicators and how we actually detect the endpoint in redox titrations. Some titrants are self-indicating, like potassium permanganate, which starts out purple and turns to a faint pink right at the endpoint. For iodine titrations, we usually use starch as an indicator. It forms a deep blue color with iodine, but that color disappears once the endpoint is reached. There are also special redox indicators, such as diphenylamine or Ferroin, which is actually a phenanthroline iron indicator. And, for samples that are turbid or have a strong color, or if the endpoint is a bit weak, we might use potentiometric or amperometric detection methods, basically relying on electrodes instead of visual cues. Now, many redox titrants actually need to be standardized before you use them. For example, potassium permanganate is often standardized against oxalic acid, or sometimes Moore's primary standards. Thiosulfate solutions, are usually standardized against potassium iodate or by using iodometric methods. Standardization, honestly, is essential because it ensures the titrant's normality or strength is accurate, which is really important for reliable results. So, let's walk through a typical redox titration procedure, step by step. First, you prepare your sample by dissolving it in an appropriate solvent and making sure the medium is either acidic, neutral, or basic, depending on what's required. Next, you add any supporting reagents, like acid or buffer, to make sure the reaction conditions are just right. If an indicator is needed, you add it now, or you might rely on a self-indicating titrant instead. Then, you start the titration by slowly adding the titrant from a burette, mixing constantly, and watching for that endpoint color change, or monitoring the instrument signal if you're using electrodes. It's important to record the initial and final burette readings carefully, so you can calculate the volume of titrant used. To make sure your results are consistent, it's a good idea to repeat the titration at least twice, aiming for concordant results. Finally, you calculate the concentration of your analyte using the equation N1V1 equals N2V2, or by applying mole-based stoichiometry. So, potassium permanganate, or KMnO₄, oxidizes ferrous ions, Fe2+, in an acidic medium. The reaction goes like this. 5 Fe2+ ions react with 1 permanganate ion and 8 protons to give 5 Fe3+ ions, 1 manganese, 2+ ion, and 4 molecules of water. In this process, 1 mole of permanganate ion actually accepts 5 electrons, so the equivalent factor is 5. Now let's look at oxalic acid standardization with potassium permanganate. The reaction is 5 molecules of oxalic acid react with 2 permanganate ions and 6 protons, producing 10 molecules of carbon dioxide, 2 manganese 2+ ions, and 8 molecules of water. Moving on to iodometric titration, let's take an example with an oxidant, which we'll call X. Here, oxidant X oxidizes iodide ions to iodine. The reaction is X plus 2 iodide ions gives X reduced in iodine. Then, the iodine formed is titrated with thiosulfate. That reaction is iodine plus 2 thiosulfate ions gives 2 iodide ions and tetrathionate ion. So, to start calculating in redox titrations, you first need to convert the titrant volume to equivalence, which is, well, equivalence equals normality of the titrant times volume of the titrant. At the endpoint, the equivalents of titrant are equal to the equivalents of analyte. If you're using molarities and stoichiometry, don't forget to account for the number of electrons transferred per mole, which is called the equivalent factor. And for most exam problems, you can usually use the formula. Normality, 1 times volume 1 equals normality, 2 times volume 2. Or you can translate everything to moles using the stoichiometric coefficients. Redox titrations have quite a few important applications in pharmacy. For example, the assay of ferrous sulfate, that's FeSO4, is commonly done using Permanganometry. Determination of hydrogen peroxide or other peroxides often relies on iodometric methods. These techniques are also used for the estimation of sulfites and nitrites, which are redox-sensitive species. You can also determine ascorbic acid, or vitamin C, by iodometry. And of course, redox titrations are essential for the assay of oxidizing impurities and for quality control of pharmaceutical formulations. So redox titrations offer high sensitivity and selectivity, when the correct reagents are used. The process is pretty rapid, and honestly, the instrumentation is relatively simple, just a burette and some reagents. Plus, many titrants are self-indicating, like potassium permanganate, for example. And yeah, they're suitable for colored or turbid samples, especially when potentiometric endpoints are used. It's really important to control pH and the medium since reaction rates and stoichiometry can change depending on the medium. Some titrations actually require heat or a specific temperature. Think about potassium permanganate versus oxalic acid, for instance. Side reactions and interfering species can cause errors, so you might need to use masking agents or separation techniques. Also, some reagents, like thiosulfate, are light-sensitive and can decompose, so make sure to store them properly and standardize them often. And, of course, safety is key. Many oxidants, such as permanganate and dichromate, are hazardous, so always handle them with care. Always standardize your titrants before use, and, check the concordance of replicate titrations. Add indicators near the expected endpoint, especially for starch. Add it towards the last portion to avoid decomposition. For colored or turbid samples, it's best to use potentiometric endpoint detection. And don't forget to record the temperature if your method requires it, since reaction rates and solubility can really depend on temperature. Redox titrations are, honestly, super versatile and essential in pharmaceutical analysis, from iron assays to peroxide tests. If you learn the principle, get familiar with common reagents like potassium permanganate, potassium dichromate, and iodine or thiosulfate, choose the right indicator, and standardize carefully, you'll be able to handle most redox titrations with confidence. Like, share, और subscribe करना ना भूलें DRX Learning Hub को. Thank you.